So a general pre-solve is a very important component in the bag of tricks for solving integer problems. The other big bag of tricks is branch and cut. Okay, so branching is an important operation. Cutting planes are very important. It turns out that pre-solving techniques are also extremely important as far as improving the performance of the solver is concerned. Okay, in fact, as the size of the model grows bigger and bigger, and lot of data for these models are generated by automated systems. These pre-solving techniques become very handy. Okay, the two important things that they do is, first of all, clean the model. And that means removing things which are redundant or unnecessary, at the same time making it possibly numerically safer or numerically better in some ways. And also to do these automatic reformulations so that it becomes tighter. Okay. And by tighter we mean that the set of solutions is still the same, but the relaxation is much closer to the set of solutions. Okay. Both parts are very important. What is meant by numerically better? So if you try to solve any linear program or nonlinear optimization problem, somewhere you might have to invert a matrix. For example, in the simplex method you have to do the B inverse, and similarly in even to verify whether a point is satisfying KKT conditions, you have to solve for lambdas, you have to find suitable lambdas, which is coming from a system of linear equations. So if that system is very poorly scaled, then it will cause numerical issues, because computers don't, or matter of fact nobody likes dividing by near zero elements or multiplying things by very big coefficients. And then also the fact that whatever numbers are stored in a computer, they are stored in double precision. That means a computer stores very roughly a double floating point number up to 16 decimal places or 16 digits of precision. And if you do repeated divisions and multiplications, then that error in the 17th place keeps blowing up, and at the end when you have done thousands of calculations or millions of calculations, that error can make a big impact. Okay, so having models that are numerically stable is very important. This part is a really this part, in my opinion, is like art. Okay, very few people actually are able to understand this part very well. Okay, because it is very unpredictable what will happen after you add so many cuts, invert some matrix, do some substitutions and so on and so forth. Okay, this part is somewhat easier to explain, and we will focus on in this lecture on this. Okay, because I don't know this part. Okay, so so we will just start looking at examples of what happens when you write a bunch of constraints in variables and try to call a solver who's trying to do some pre-solve. Okay, so again, if you have several constraints, it would be nicer if we can throw out many of the constraints which are not important for finding the solution. Okay. So if there could be some way to say that, out of these 10,000 constraints, these 2,000 constraints are not really needed, then we can throw them out. So such constraints are also called redundant constraints. A redundant constraint is a constraint which, if you remove, the feasible region doesn't change. Okay, so you can safely remove those constraints. Okay. The easiest check for a redundant constraint is to check for duplicacy. Okay, so sometimes if you have in your large model, if you have a constraint then obviously you may want to remove one. Okay, and this is good even for the linear programming relaxation, because in every iteration it doesn't have to compute some coefficients or check whether the slack of this variable is going to enter or this is going to enter the basis. Okay. This is somewhat easier to check because all you have to do is see how many variables are there in both constraints, whether the right hand sides are same, whether the coefficients are same. It's a simple test. Okay. So when you write such routines, you also need to see how many iterations or steps these routines are going to take. So for example, suppose I give you 1,000 constraints and I ask you, can you find all such duplicate constraints? Then you have to compare 1,000 constraints with every other constraint. So and choose 2 type of comparisons. So you have to be little bit smart in how you do it, because 1,000 choose 2 is close to 500,000 or something. Okay. A slightly different version of this when one constraint is actually a multiple of the other constraint. So even here, it is very easy to see that we can safely drop one constraint and nothing changes. Okay, so that can also be tried, and it is relatively easy to do. Okay, little bit more difficult is to detect whether some constraints are combinations of other constraints already. Okay, so for example, suppose I have these 2 constraints. Now they are not duplicate of each other, but suppose I have a third constraint which is just the sum of these 2 constraints. Okay, now this is not a redundant constraint, this is not, but this is, okay, because this is just a combination of these 2 constraints. Okay, these are somewhat more difficult to detect. Okay, because this constraint could have been a combination of 4 constraints or 10 constraints or many other constraints, and the number of combinations you can try is just too many. Okay, and the advantage is not that great. Okay, so there is some trade-off in what all you want to check and what all you want to clean up. Okay, sometimes such redundancy is detected while solving the problem. So for example, while solving this a linear program, sometimes you can check that the slack of a certain variable is always basic. That means that constraint is never going to be active in your set, then you can drop it. Okay. All right, any questions so far? No. Okay, so this is one. A similar exercise to this is when you check for duplicate variables. Okay, these are very basic house cleaning type of activities, which are very important. Okay, and quite tedious to implement actually. All right. So if you have, two variables which always occur together in all constraints, linear constraints, and with same coefficients, then you can combine them together as one single variable. Okay, so suppose x1 plus x2 appears in all constraints simultaneously, always together. Then you can just say that x1 plus x2 is some other new variable w1 and have one variable less. And once you have solved the problem, then you find what are x1 and x2 out by looking at w. Okay, so that is also pretty straightforward to do. Okay. Slightly more important and tedious thing is bound tightening. So there are two things to do here. One is to find tighter bounds on the range that a variable can take. Okay, so suppose I am able to say that the simplest case is this. For example, suppose I say that x1 is between 0.9, or let us say y1 is between 0.9 and say 0, okay, and y1 integer. Then I can immediately tighten this bound to 0, okay, because there is no other integer possible. Okay, so that is one extreme case. But you can also tighten bounds for many other variables in the following way. For example, suppose I have again a very simple example, and all x's are greater than equal to 0. So from this constraint, I can say that x1 can at most be 10, x1 can at most be 5, and x3 can at most be 2. Okay, so I get some range of each variable. Okay, this is 2x2, sorry. Okay, all right. So very simple. Just this is some sort of interval analysis where you say, what are the lower bounds of each variables, what is the upper bound on each constraint, do some subtraction and division, and you get it. Okay. Similarly, if this was negative, you can possibly try to find lower bound of x3 or something. Okay. So from each constraint, you can derive the bounds on the variables. Okay. And when you tighten these bounds, it is possible that some of the integer variables will see some bound reduction, and then you can quickly fix them up. Okay, so that helps sometimes. The other side of bound tightening is to actually deduce redundancy in a constraint. So for example, suppose I say that I have again this constraint and every x is between 0 and 1, then clearly this constraint is redundant. Okay, because the maximum this can take is value 8, but it is saying less than equal to 10. So even if I drop this constraint, nothing really changes. Okay, so I can safely remove this constraint. All right. So so in bound tightening, you can do both. You can tighten bounds of variables, and using bounds on variables, you can detect some redundancy. You can also detect infeasibility sometimes. Okay. So for example, if this was greater than equal to 10, then you know that this problem is infeasible. Okay, because the maximum this can take is 8, but the right hand side wants it to be more than 10. Okay. Okay, so an important idea is this dual fixing of variables. It is quite intuitive. So I'll just give you some example. Minimize, suppose I say minimize 5x1 plus some other expressions, and everywhere x1 has a positive coefficient with a less than equal to sign. So suppose I say 3x1 plus something something less than equal to 1 minus 2x1 something greater than 3 and x1 less than. So in every constraint we are actually trying to keep x1 as low as possible, and even the objective function wants x1 to be as low as possible. So I can safely set x1 to its lower bound, okay, and fix it and remove it entirely from the model. Okay, this is called dual fixing, because if you write the dual, that corresponding constraint might turn out to be redundant, and you can delete that constraint. That means you can fix that variable. Okay. Any questions so far?
This is the one I think that you can't use in NLO branch and bound, because the nonlinear objective may not have that property.
For this, you need to know all constraints beforehand.
Yeah,
if you have some constraints hidden which will appear later, they might have the wrong coefficient.
Yeah.
And then you would have fixed a variable which you should not have fixed. Okay, so this you have to take care if you are doing only on a subset of constraints. Okay, not all constraints. Okay. Huh. You can set x1 to its, so whatever is the lower bound. So suppose x1 is between 3 and 8, then you can say x1 has to be 3. There is no point in setting it to a higher value. Yeah. Okay. Two tricks I already showed regarding integer programming. One was the aggregation of those constraints, where I said instead of having k plus 1 constraint, we can have just one constraint. And the other one was disaggregation, like happens in facility location, where you have a big M constraint, instead you write it as a collection of smaller many constraints. Okay, so those are also important tricks. One important thing which is quite easy to see is called coefficient improvement, and I'll just give an example of how it works. So assume we have this set of constraints. So x1 plus 11y1 less than equal to 20, and x1 is between 0 and 14, and y1 is binary. Okay. So none of these constraints are redundant, and you can't use other simplifications. But if you stare at it for a little bit or draw the picture, then many things become clear. So without drawing the picture, what happens when y1 is equal to 0? Okay, I get the first constraint changes to x1 less than equal to 20, which is redundant. Okay, but it is not redundant when y1 is 1. Okay, so when y1 is 1, it implies x1 less than equal to 9. Okay, so this is not really a redundant constraint, and I can't throw it off. Okay, but but this part can be tightened. Okay, see, I can try to change this constraint so that when y is equal to 0, this constraint actually becomes tight. Okay, so what I'm going to do is subtract delta from both sides. Okay, so remember that when y1 is equal to 1, this constraint is actually important. Okay, so when y1 is 1 and I subtract delta from this side, then I should subtract delta from here also, when y1 is 1. Okay, but when y1 is 0, I don't need to subtract anything here. Okay, but since there is redundancy on this side, okay, I can still subtract something when y1 is 0. Okay, how much can I subtract when y1 is 0? 6 units. Okay, because this is 20 and I can go down to 14. Okay, so I will change this to, instead of this constraint, I will change it to x1 plus, so I'll subtract 6 from here and also 6 from here. So this will become 5y1 less than equal to 14. Okay, so I'm just going to rewrite it again. When y1 is equal to 1, we want x1 to be less than or equal to 9. Okay, and instead of this constraint, if I replace this constraint by this one, my set remains the same. Okay, because when y1 is 0, I still have a redundant constraint, and when y1 is 1, I have x1 less than 9, and same here. Okay, so here both S1 and S2 are same, but if you draw a geometric picture, you will see that this is actually tighter. Okay, you will see a picture like this. Okay, so this is R1, this is R2. Okay, feasible region is somewhere here. Okay, all right. So this is called coefficient improvement. Because you are playing around with the coefficients of some binary variables. Okay, and you can have many cases. Okay, so sometimes it's not necessary that the constraint has to be redundant when y1 is 0. Sometimes they are redundant when y1 is 1. So then you have to turn the coefficients in the other direction. Okay, so there are a lot of these if then else cases which you have to take care when you are implementing such things. Okay. In this constraint, it was obvious that we can try to improve coefficients based on y1. Okay, that is not always the case. So let's look at this last example before we stop. Suppose we have yeah. Huh? Huh. Trick exactly is, so you say that I'm going to change this by delta. So I'm going to change this by delta and this also by delta. And then you have to find the maximum possible delta which is still allowed. Okay. And in this case, the maximum possible delta is 5. Okay. So some.
But if you have many real constraints,
Huh.
real variables,
Huh.
and in that case, if you want Titan, you have to do it for each one of them.
Yes. So if you have a very big constraint with say 100 variables, so you can take some shortcuts because these coefficient improvements are usually possible when you have some big coefficients. If all your coefficients are plus minus 1, then it is unlikely that you will be able to improve them.
Some of them are small, but some of them are
So you try on the big ones. Okay, it's a practical issue, where you want to focus your energy and get the maximum out of it. Okay, but this has big advantage. In implementation, it really reduces the tree size a lot because you are tightening up things. Okay, this is actually the convex hull of this set. Okay. This also works in nonlinear settings. So instead of x1, suppose you have just f of x1, and if you set y1 to 0, then you have to check whether fx1 less than equal to 20 is redundant or not. So you need some bound on f. Okay. So by looking at that computational graph that we will come to in the next week when we do global optimization, you can actually get bounds on f based on bounds on variables, and conversely we can get bounds on variables based on bounds on f. Okay. So that is reverse propagation. So both are possible. Okay. All right. So I'll just give you one more example where it is a little bit more tedious to check whether such improvements are possible. So suppose I have an constraint. Let me see where I wrote. Okay. Okay. So let me just cook it up. Okay. So 15x1 plus 12x2 less than equal to, let's say, 40, and x less than equal to 1 and 0. Okay. Or let's make it 32. Okay. So this constraint is not really redundant. Okay. But if I have an additional constraint, x1 less than equal to let's say 10y1 and x2 less than equal to 10 or 12y1. Okay. So if I have this set of constraints, then I know that when y1 is 0, this constraint is redundant, and when y1 is 1, this constraint is still redundant. Okay. So that means this constraint can be dropped safely. Okay. So even though in itself this is not a redundant, if I don't look at other constraints, this looks like a useful constraint to have, or an important constraint not to leave out. But under the influence of y1, this is actually redundant. Okay. So these are called indicator variables, and if I have a map of which indicator variables influence which constraints, then I can try to guess that this will always be redundant no matter what y1 is. Okay. So I can drop it. Okay. y1 as always is integer. Okay. So y1 is, I should have written. Okay. So this is a redundant constraint. Okay. And similarly, if this was
So can you again explain when y1 is 1?
When y1 is 1, x1 can take value up to 10 and x2 can take value up to 12. So the maximum, I mean this has some coefficients also. So I'm sorry. So suppose this is just plain, something like this. Okay. So then you can remove them. Okay. No, not a constraint. Okay. So let's say 100 or something. Okay. I'm sorry. I should have written in my notes. Okay. So so this can be done. Okay. So similarly, we can do coefficient improvement on constraints. Okay. So even so here this this y1 was explicitly in the constraint and I could improve its coefficients. But sometimes it is possible that this is actually 0 and it is not in this constraint, but it is influencing the variables of this constraint by some other indicator constraints. Okay, then we can introduce that extra y1 and still do it. Okay. So, so these are some of the tricks which are quite standard and been around for about 20-30 years. So a good paper to read is by Savelsberg in 1991 as a starting point of these bag of tricks. Okay, some of these are relatively straightforward, extensible to in nonlinear case, but not all. Okay, so for example, duplicate nonlinear variables, I don't know what you can try to do. Okay. After this, there have been quite a few other papers, but this is a good starting point to look at things. Okay. So with that, we will stop. All right.